Going to, the other hat that you wear as director of the Institute for Artificial Intelligence and Fundamental Interactions.
And I'll use this opportunity to take a sip from the mug so you can see the IAIFI
There we
logo
go.
here.
Could you share more about the origin story of this organization and what its mission is?
This actually goes back to 2016 when a number of my friends were using AI or starting to use AI for particle physics applications. So around that time, you were seeing incredible advances in computer vision. And so particle physicists were taking advantage of that to try to apply it to data analysis tasks at the LHC. And in 2016, I'm on the record as making the following joke, all the stuff going on in the world of deep learning, why are my theory friends doing this? We're in the business of deep thinking. And that was a joke that I made in 2016, quite dismissive of what was happening in the AI world. And if I'm really honest with myself, it was really that I was feeling threatened because a lot of the theoretical work that I was doing was being supplanted by AI advances, such that I was developing new data analysis techniques. But AI was in some sense developing its own techniques that were direct competition with my work. And indeed, my work is often used as a punching bag for AI benchmarks where you say, how much can you beat Jesse's strategy? So that's what was going on in 2016. And at that time, that fall, two graduate students, Eric Metodiev and Patrick Kamitsky, came into my office. They were new graduate students, really excited about using AI and applying it to physics. And I was quite dismissive of the work that they were doing. And I was telling them all the things about their research program that didn't make sense from my theoretical perspective. And I thought I'd never see them again. I was kind of, get off my lawn, curmudgeon style. But they actually continued to do their PhD work with me, and they showed me the way that AI gives us new perspectives on problems in particle physics. And now there are things that I can't unsee. That is, the way that machine learning and AI gives you a different lens on your problems are ones where I really see that as the future of how we do scientific investigations. So that started in 2016. I went on sabbatical, and that sabbatical a few years later really cemented my excitement about AI. And then coming back from sabbatical, there was a call from the National Science Foundation to launch new AI institutes. And so folks at MIT, along with Harvard, Northeastern, and Tufts universities, we got together and put in a proposal that ultimately was funded with me as the director of this institute. And that joke that I had before about deep learning and deep thinking, the tagline of IAIFI now is deep learning plus deep thinking equals a deeper understanding. Both a deeper understanding of physical systems, but also a deeper understanding of how AI itself works. And so people know, or at least have some conception of what deep learning is. This is this AI revolution. Deep thinking are all the things that I learned as a student in physics, the way that you analyze complex systems, break them down into the fundamental pieces, things like symmetries that we teach all MIT students about in their classes. And you take those physics insights, you combine them with the AI revolution, and indeed we have seen a deeper understanding coming out of our institute. But it started off with me being very suspicious about AI and dismissive, honestly. And then my perspective transformed, and now I'm very much an evangelist for this toolbox of advances from mathematics, statistics, and computer science, kind of under this broad umbrella of AI, and what the potential of that is for scientific advancement.
Well, in a way, spoken like a true scientist. When given some data that opposed your viewpoint, you then updated accordingly. Okay. So I want to get into both of those parts, what AI is doing for physics and what physics is doing for AI. So maybe just starting with the first one, could you describe some interesting breakthrough or just novel approach that you've seen where AI has really been leveraged to maybe help with looking through and sifting through that data from the LHC or other experiments?
Right. So we talked before about this synergy between experimental work and theoretical work. And the bridge between experiment and theory is known as inference. So inference is the process of given data to try to, as best as you can, figure out what the underlying theoretical description is. And what AI has done is allowed us to do much more sophisticated inference techniques that can take maximal benefit from the data that we've collected and apply it in much more sophisticated ways to theory. And so when I was a graduate student, what you would see plots coming out of colliders, despite the fact that you have this massive amount of data. All the data was kind of compressed onto a histogram. One dimension, you make some plot, you see some bump, you declare victory, but one dimension. This massive high-dimensional data set being projected down just to one dimension. With AI, you can really work with that entire high-dimensional feature space, all the intricate information from that collision debris, and use that to do inference. And so, whether you would call it machine learning or AI at the time, certainly the discovery of the Higgs boson was aided by various AI-style techniques, and arguably we discovered the Higgs boson faster than people thought because you were taking advantage of AI's ability to find those complicated patterns. But now, more recently, you're now seeing heroic analyses where you can do this theory experiment comparison in ways that are way more sophisticated because you have this ability to, well, even though we as humans can't visualize that high-dimensional spaces, the AI can, and it can make decisions about what is or is not most likely in the universe based on this full high-dimensional space. So that's one of the ways that the AI, in a very concrete way, is affecting particle physics. But it's also affecting things conceptually. And people are now starting to ask questions that you wouldn't really ask before because you didn't have the language to talk about it. And so let me tell you one example from my own research. The standard model of particle physics, the fundamental ingredients involve particles known as quarks. And quarks are the constituents of the proton, but you've never seen a quark in isolation. Quarks carry the strong nuclear force, and the strong nuclear force is itself carried by the gluon. And so quarks and gluons are the fundamental ingredients of the standard model, and yet nothing in our collider data tells us about, oh yes, that's a quark, that's a gluon. It's just coming from an inference process. But with the help of AI, you can actually now study the properties of quarks and gluons kind of independent of the theory, and then separately do a theory comparison. So instead of just having to infer directly onto quarks and gluons, you can kind of have this intermediate stage where you can study quarks and gluons in quotes, but without ever having to make any reference to quantum field theory, and then check whether the properties that you've inferred from that does indeed have the bridge that you'd like to the theory land. So it's a way of processing data in a way that can be more agnostic as to the underlying description. Again, I'm still a theoretical physicist. I still want to compare to the theoretical model, but there's a lot more that I can do within the data itself to tease out its structures with the help of AI.
In a previous episode of this podcast, I interviewed an investigator at the ARC Institute. It's a funded organization that does really interesting work in building foundation models for biology. And they build the self-proclaimed largest ever model in biology, EVO2, released it a couple of months ago. And in talking with them, they had a partnership with NVIDIA. Also, Greg Brockman, co-founder of OpenAI, helped out with the team. And one of the things that I learned is, in getting this model to be developed and to work, there was almost just as much effort in the structural engineering of being able to, for example, take this many GPUs and make them work together to be able to do training on these models in order for them to, be able to break down the model into its component parts and still train it as a whole model. And having OpenAI's, for example, expertise in that was really valuable to the ARC Institute. I'm wondering, as you've seen the application of AI for physics, you talked about, the petabytes, exabytes of data coming out of the LHC, needing to put that onto magnetic tape just because of the volume of data. How much of the challenge is around, coming up with interesting new algorithms that are more useful and clever versus just the engineering of, building the right, size, cloud computation facility in order to make this work happen?
Right. So there's kind of two different aspects of it. One aspect of it is indeed the infrastructure aspect. But in particle physics, where we're operating is so far different than what's happening in the more commercial realm that we are leading the way in developing the AI toolbox because we need things that are faster and more robust than anything that's really needed in an industry context. So there's an effort in fast machine learning where you're trying to make a machine learning that can operate at this trigger decision level at the LHC to try to decide whether or not to keep events. And that's something where we are at the forefront, that we are developing techniques that are now applicable elsewhere. The other aspect, which is, I think we don't really know which way it's going to go, is this, in some sense, the tension between deep learning and deep thinking. That there is certainly advances that are happening by just throwing a lot of GPUs at the problem. And I'm always shocked how much how well things scale by just putting more compute at the problem, or more data at the problem, how things improve. But there's also like the deep thinking part, that embedding your physics knowledge into the AI. And that's an interesting type of trade-off, because if you're doing things on the more compute end of the spectrum, yes, you can benefit from industry advances. If you're building custom AI tools that have physics knowledge built in, that's harder to benefit from industry advances, but then you are kind of guaranteed that you have the physics knowledge in your AI architecture. And I think that's where it becomes a very interesting trade-off. And I think we're still deciding to what extent is domain knowledge relevant or not. It probably really will depend ultimately on the quality and the availability of the data to see which kind of technique wins out. But a lot of the work that I do, it even runs on laptops. You don't actually need super fancy, big GPU infrastructure. And yet it's still impactful. And that's an interesting thing that happens when you actually do bake in physics knowledge, that oftentimes you can have the training be more efficient than you would if you didn't have that physics knowledge to begin with.
Well, I think that's really exciting. Also, just from, I went to the Sloan School here at MIT and always thinking through things on the business end of things. And as you are, in a way, one of the things we talk about is extreme users in different areas. As you're an extreme user of data and sensors and so forth, some of the breakthroughs that you need to have in order to be able to do your work, I imagine, have really interesting applications, whether they're top of mind right now or going to be top of mind in the next few years, right? You talk about making quick decisions. Well, I think about, robotics that have embedded AI systems that themselves need to make quick decisions with data that comes in. What parallels are there? So yeah, how do you think about that?
The work that I do is curiosity driven. And I certainly am not doing my research with an idea about how it might be used elsewhere. But it is pretty remarkable how techniques that you develop with a particular physics context in mind end up being relevant in other applications. And one way of thinking about it is that for us, we have to develop the technology. Otherwise, what we do doesn't work at all. Whereas in other contexts, there's a trade-off, and there may be multiple technologies that you're deciding between. But if someone gave you as a gift something coming from the curiosity-driven realm and said, hey, here's this new technique, then of course you would adopt it. And that's what we've seen with various technologies that have been developed in particle physics, independent of AI. And now we're starting to see it more with AI, in particular with fast machine learning, where fast machine learning is relevant to a variety of disciplines, obviously not just in physics. Now, we happen to have the most extreme needs on time, but you can scale those things back and of course is relevant beyond there. And it ends up being an interesting question. If you knew ahead of time that your goal was to develop that technology, would you nevertheless still want to fund the curiosity-driven research to make that happen? And I don't know the answer, but I am always amazed about some of the practical applications of the work that we do in physics that can be quite different from what our intended original application was.